Hello everyone, welcome to Catalysis by Vedantu. My name is Pahul and today we are going to do the third class of the solid state chapter. The previous class, if you guys attended it with me, it was a long class, right? We learned a lot of new concepts in that class. We saw a lot of visualizations. Now today's class, on the other hand, is going to be really chilled out. The concepts that we're going to learn today are very important, by the way. A lot of questions directly are asked from these concepts time and again in all the competitive examinations. But these concepts are relatively easier and we just need to understand the pattern and we're good to go for the entire class, alright? So the things that we will focus on today are these. Rank. What is rank? Okay, so let's start understanding these terminologies and then we will take these terminologies to individual types of unit cells and we'll figure out what they are for every type of unit cell. Okay, so what do we mean by rank? Rank basically means the number of atoms inside a unit cell. Please make sure you are writing all of this down along with me. Please keep taking notes because taking notes is important. I've told you that time and again. Density. What is density? Density basically is just mass upon volume, right? And we will do this for the unit cells. You remember the volume of the unit cell? If it's a cubic unit cell, the volume of the unit cell will just be edge length cubed, right? We'll see that in a while again. Then comes the volume of atoms inside the unit cell. There'll be a certain number of atoms in the unit cell, certain number of effective atoms in the unit cell. We will need to figure out what's the volume of those. Pretty self-explanatory, right? And then we come to the volume of the unit cell itself. Same thing. Edge length cubed. And finally, we'll come to something very interesting called packing efficiency. Let me give you an idea of this. Well, let's say you have a bag or a backpack of 30 liters. Whenever you buy a bag or a backpack, it always says that the capacity of the bag is this liters, okay? So 30 liters, let's say, is the capacity of your bag. Now, imagine you are just stuffing it with clothes, okay? You're just stuffing it with clothes and once the clothes are stuffed inside, you take it. Then you realize after your trip is over that you've purchased a lot of new things. Yeah, and because you've purchased a lot of new things, you have to still stuff it into the same bag, right? So what do? You squeeze the clothes, you fold them better, you roll them tightly, you put them in a corner. So initially, my dear friends, what had happened is that you did not utilize 100% space of the backpack. Yes, you just randomly threw your clothes in the bag. And since they were not arranged in a very well manner, a lot of space was empty inside the bag, right? So let's say out of the 30 liters in that initial packing that you did before you went to the trip, you were able to occupy only, let's say, 10 liters. Okay, because of your weird style of packing, you just threw clothes here and there, some empty gaps over there between the clothes, etc., etc. So there was still 20 liters of space that was not occupied. So my dear friends, over here, what is the packing efficiency? How much of the initial space were you able to utilize? Can I say that you were able to utilize 1/3 of the space? 1/3 of the bag was utilized, isn't it? Makes sense? 1/3 can also be written as 30%. That also works. So 30% was your packing efficiency. Okay, 30% was your packing efficiency. Fine. Now, my dear friends, let's say at the end of the trip, out of the 30 liters, you could occupy, let's say, 30 liters. Okay, let's say you filled up the entire bag with stuff. So now what is the packing efficiency? Now the packing efficiency is 100%. Getting the idea? Packing efficiency is basically the percentage or the fraction of the available space that you were able to utilize properly. Now, if you remember, in unit cells, there are certain number of atoms. They occupy a certain amount of space. So depending on what kind of unit cell we have, atoms would occupy a certain amount of space, and certain amount of space would be vacant, unoccupied, empty. So what we will find out in each of these unit cells is what is the efficiency with which the atoms have occupied the unit cell, and that, my dear friends, is packing efficiency. So all of these points, all of these quantities, we shall define for different unit cells in today's class eventually. Now, moving on, let's look at this question first, and then we'll move on to the different unit cells. There's a question that I gave as a homework in the previous class. I think 3 or 4 people gave me the correct answer in the previous class's comment section because everyone else, I don't think they even waited till the end of the class for this homework. But anyway, for those of you who did, a compound formed by elements X and Y has a cubic structure in which X atoms are at the corners. So these are all X atoms marked in red color. And the first half of the question we had done in the previous class. So I'll just quickly mark these. Very nice. So effectively, what's the number of X that we have over here? There's just one X, right? And we have been given in the question itself that there are 2 atoms of Y at each body diagonal of the cube. These are the body diagonals. Ignore the midpoint over here that is given. Ignore that. So where are my Y's present? 1, 2, 3, 4, 5, 6, 7 and 8. Right? 2 Y's at each body diagonal. We had realized that the entire structure needs to be symmetrical. So if you divide the body diagonal into 2 halves, midpoints of those 2 halves will be occupied by Y. Okay, so this was the thing that we had come up with in the previous class, and for the first part, the formula becomes XY8. Great. If all atoms from one body diagonal of the cube except corners are removed, calculate the effective. Very simple, right? Done. This is it. We don't have to remove the corners, but we have to remove the atoms along one body diagonal. What's the remaining formula? Done. Simple? Yeah. It's an extremely simple question. And I'm sure a lot of you will be able to do it in the first go. But you know what? People hardly ever associate chemistry with imagination, chemistry with geometrical drawings. And therefore, believe it or not, a lot of students wouldn't be able to solve this question if it came in their examination. So if you are able to understand the science behind this question, very good. Now, my dear friends, let's move on to this particular unit cell. What kind of a unit cell is it? Everyone, we have understood this in the previous class. Okay, so for the rest of the analysis of this chapter, we will only consider cubic unit cells. All the others, monoclinic, triclinic, orthorhombic, etc., all of those 7 unit cells, only cubic is easy enough for us to understand for the domain of our syllabus. So only one cubic will be studied throughout the rest of this chapter. Maybe hexagonal here and there. Fine. The remaining 6 3-dimensional unit cells, our study of those is done. Questions from them can still be asked. In this year JEE in 2023, there was a question asked from, the examples of the unit cells. So basically they had asked that in which of the following 3D crystal systems can body-centered cubic exist? So they had given all the crystal systems. So basically they had given cubic, orthorhombic, monoclinic, triclinic, hexagonal, etc. And you had to choose out of them in which can you realistically have body-centered cases. I had given you a table in the last class. You can revise that from there. But for the rest of the chapter, we will only stick to cubic unit cells. Fine. Which means that in cubic unit cells, A is equal to B is equal to C. Edge lengths are the same. Alpha equal to beta equal to gamma equal to 90 degree. All the interfacial angles are 90 degrees. Fine. So very simply over here, can I just call it E? A is equal to B is equal to C. So let's just call it E, edge or edge length. Fine. So my dear friends, if I have a cubic unit cell, no matter what is the, no matter how it is occupied, no matter what the lattice points are, if I have a cubic unit cell, can you tell me what will be the volume of the cubic unit cell? E cube. If you don't remember this, then please enroll yourself back into nursery class. Do your entire math schooling again. Because this is basic geometry, right? Fine. Okay. Enough of pathetic jokes. So now over here, the system that we have, do you realize that atoms are present only at the corners in this unit cell? This is the ball stick model. This is the space fill model. This is the space fill model removing the sections that are not inside the unit cell. All of this has been discussed in the previous class. So now, since only corners are occupied, can I say that this is a primitive unit cell? There were two types of unit cell fillings. One was primitive, where the atoms were present only at the corners, and the other was centered. In centered, you had three cases: body centered, face centered, and end centered. So this one is the primitive case. We also call it the simple case. We are simplifying the word primitive by calling it simple. So this is the simple cubic cell. Okay, you can call it the primitive cubic cell, or you can call it the simple cubic cell, SCC, simple cubic cell. Okay, simple cubic cell. Fine. Now in simple cubic, what is the rank? Rank means the number of atoms inside the unit cell. A lot of you would say, sir, 1, 2, 3, 4, 5, 6, 7, 8. No, not 8. Because there are portions of all of these atoms outside the unit cell. Only certain portions are inside. And I'm sure you remember from the last class that the contribution, okay, of each corner atom is equal to 1/8, right? This portion that is inside the cube is only 1/8 of the entire atom. This is an imaginary unit cell. The lattice is already there. We are just trying to envision the smallest repeating unit. We can imagine that. We don't need to actually cut it into this piece. This is just for our imagination so that we can understand the entire lattice well. Right? So over here, contribution of each corner atom is 1/8. How many corner atoms are there? Number of corner atoms equal to 8. So total, how much do we have? Number of corner atoms is 8 into the contribution, that is 1/8. So my dear friends, effectively the total number of atoms inside this unit cell is equal to 1. So the rank of simple cubic is 1. Simple cubic. ठीक है जी, चलो ये सब हटाते हैं यहाँ से. Let's remove this. Now let's talk about density. Let's talk about density. Density is what? Mass upon volume. Isn't it? So for the simple cubic case, what's the volume? We know what's the volume. The volume is just edge cubed. What will be the mass? The mass will be 1 times the mass of this atom. 1, that is the rank. There are 1 atoms inside this unit cell, right? I'm calling it out explicitly because in other unit cells the number will be different. Okay. So since there is just 1 atom over here, 1 into mass of the atom. Okay. Now my dear friends, you have to ensure that you take care of the units over here. Alright. Units are important. What do I mean by this? Let us say I give you a specific case. Okay? I'll give you a specific case where I'll say mass of the atom is X atomic mass units. So what does that imply, people? That implies that the mass of one atom is X atomic mass units. Can I Therefore, using the mole concept, say that mass of 1 mole of these atoms is equal to X grams. Whatever is applicable in atomic mass units for one atom is applicable in grams for 1 mole of atoms, right? So the mass of one atom is X atomic mass units, but what is the mass of one atom in grams? We can calculate it from here, right? So the mass of one atom in grams, okay, the mass of one atom in grams is basically equal to X divided by mole. This is for 1 mole of atoms. So for one atom, X divided by 1 mole. What is mole? The Avogadro number. Yeah, 6.022 into 10 to the power 23 grams. Fine. Very simple. Basic concepts of chemistry. Mass of one atom in grams would be X. That is the mass of one atom in atomic mass units divided by the Avogadro's number. Simple. Okay. So, if I have to take the mass of an atom in grams, I have to be careful of the units. That's all I'm saying. Whenever there is a question, you have to be careful how to take the mass. We'll see an example today, later. Okay. Now, there's a certain formula of density that you will find in books. Okay. I'll show you what that formula is. Okay. So, mass inside any unit cell would basically be equal to the rank of the unit cell into the mass of the unit cell, the mass of the atom in AMU. If I have to take this in grams, I have to divide the mass in AMU by the Avogadro's number. And of course, since I have to divide by volume, the volume is H cube. So my dear friends, this is a formula that you will find in your notebooks. Okay. This is a formula that you will find in your notebooks, in your textbooks, by the way, not notebooks. So rank sometimes is written as Z. Mass in atomic mass units is sometimes referred to as W. Edge length is edge length. So E cube into NA. Now the problem with this formula is that it looks very cryptic. It looks very complicated, for the lack of better words. So what a lot of students end up doing is that they try to remember this formula. They try to cram up the formula without understanding the logic that density is just mass per volume, right? So this is enough for you to solve questions in your exams. No need to remember this, okay? Anyway, so density is just mass per volume, and I'm sure all of us can calculate that when the time comes for it. Now, what will be the volume of the atoms? See, our assumption over here is that atoms are spherical in nature. Our assumption is that the atoms are spherical in nature. Fine. So, what's the volume of the atoms? Let us say that this is the radius of the atom, R. Can you see very well that that's the radius of the atom? Isn't it? This is the midpoint of the sphere. This is the terminal point of the sphere. So that is a radius. What is the volume of a sphere? Volume of a sphere is 4 upon 3 pi r cube. Everyone knows that. Okay. So volume of the atoms is 4 upon 3 pi r cube. But do you realize that the volume of the atom, I mean the radius of the atom, defining the radius of the atom is very difficult. It's a very difficult thing to define the radius of the atom, but since we have demarcated a proper unit cell over here, it is simple for me to define the edge length of the unit cell. I took an entire lattice, I found the smallest repeating unit. I can easily define its edge length. And in questions, sometimes radius will be given, sometimes edge length will be given. How do you find either of these in the laboratory? This is found by X-ray diffraction. This, there are multiple ways of defining it. You basically remember the chemical bonding chapter where we were trying to define different type of radii, ionic radius, covalent radius, metallic radius, etc., etc. Yes. So that is an analysis that is done to find out the radius of an atom. It's different in different scenarios. Please revise chemical bonding if you've forgotten about that. Yeah. So basically spectroscopy and X-ray diffraction are the techniques that help us figure these values out in the laboratory. But for your analysis, one of these values will be given to you in the question. Fine. So over here in the case of a simple cubic unit cell, can you very easily notice that R is equal to edge length divided by 2? It's a very simple observation, right? Edge length, radius, half of the edge length is radius. ठीक है ना? तो यहाँ पे instead of R, let's fill E by 2. So this is basically equal to 4 upon 3 pi, R is what? E by 2 cube. You can simplify it if you want. E cube by 8. So this is pi E cube by 6. In case you want to simplify it till that extent. Not necessary. We are smart enough to understand the volume of the atoms. So ये यहाँ पे, let's keep it in our minds. Volume of the atoms is this much. Volume of the unit cell we all know is E cube. Too many times we've understood this. Now what is the packing efficiency, people? Packing efficiency is the fraction of the total volume that you have occupied. Yes? Occupied volume, this is the volume occupied by the atoms. And this is the total volume, yes? Do you see that there's a bunch of empty space over here? Yeah? This space that I'm trying to highlight is the empty space inside the unit cell. Why is it empty? Because the atoms are considered as spherical, right? So there would be certain amount of space that the spheres can occupy, but once you have put them together, there is obviously going to be some empty space, right? Limited by the geometry of the spheres itself. Fine. So my dear friends, over here, packing efficiency is basically going to be calculated like this. Occupied volume, that is the volume of the spheres combined together. Occupied volume divided by the total volume. तो कितना आ गया ये? What's the occupied volume? Pi E cube by 6, and this has to be divided by total volume, which is E cube. E cube and E cube cancel out. So the packing efficiency, the packing fraction over here is equal to pi by 6. And my dear friends, if I have to calculate a percentage packing efficiency, what will I do? To convert a fraction into percentage, I'll just multiply it with 100. So my dear friends, how much does this number come out to be? Can you tell me quickly? This comes out to be 52.36%. So essentially, what this means is that inside a simple cubic unit cell, the occupied space is around 52.36%. The remaining is empty space. So the efficiency of packing inside a simple cubic unit cell is 52.36%. This is a value that you have to remember, okay? This is a value that you have to remember. What is this? This is, again as I said, all of them are cubic. Can you see this is a face-centered cubic? Face-centered cubic unit cell. What will we call it? We'll call it FCC. Perfecto. What's the rank now? We'll do this quickly. What's the rank? There are 8 atoms at the corners, and the contribution of every atom at the corner is going to be 1/8. So this is for the corners. Okay? And this has to be added to the atoms that are present at the faces, isn't it? Sometimes the pen doesn't want to switch properly. Now both the blue pen and the red pen are selected. So sometimes it will come out to be red, sometimes it will come out to be blue. I don't know who designed this. Whoever did needs to rethink. Anyway, so for the face-centered atoms, okay. So how many faces are there? There are 6 faces. So there are 6 atoms at each face. I mean, total, there are 6 face-centered atoms. 1, atom at each face center. So how many of those are there? 1, 2, 3, 4, 5 and 6. Yes. Okay. 6 face-centered atoms, and the contribution of each of them, as we had learnt in the previous class, and you can very well see here, half of the sphere is inside the unit cell, half of it is outside the unit cell, which we've cut over here in the imaginary space fill diagram. How much does it come out to be? 1 plus 3, that is 4. So the rank of a face-centered cubic unit cell is equal to 4. There are certain lattices in nature which will basically have the face-centered cubic as its repeating unit. Okay? The way it's arranged, basically when you carve out a unit cell, you will find that inside the unit cell you have effectively 4 atoms. Okay? What kind of a lattice is formed? That depends on experimental evidence. Okay, different substances form different types of crystal lattices. And you'll be like, sir, but how do we figure out which kind of a system occupies which kind of a lattice? I mean, that's not for us to understand. That's just how nature has built it. Crystals are already existent in nature. What you have to do is take a certain crystal. Let's say you take NaCl crystal. Let's say you take copper solid. Its small amount is, copper is basically crystalline, right? Metallic solid. Or you can take zinc sulfide, calcium fluoride, etc., etc. So you take a sample from nature, you do some experiments on it. Okay, X-ray crystallography is a very nice technique these days that can help you decipher the structure of the solid state. And after those experiments, after these calculations, if you can figure out the density of the entire substance, density can be figured out for any amount of substance, right? Mass per unit volume. So if you can figure out the density, if you can figure out the packing efficiency, etc., you can then figure out what kind of unit cell it is. Slowly and steadily with questions, you will understand the point more. But the thing is that we don't know from our understanding as a human what substance, what atom, what element will occupy what kind of lattice, will have what kind of a unit cell. We don't know. We can only see the existing crystals that are there inside nature, conduct some experiments on them and see, this one follows face-centered cubic unit cell. Okay, this one forms a simple cubic unit cell. Okay, this one forms a body-centered cubic cell. Oh, this one forms a monoclinic cell, etc., etc. Fine. Coming back over here, if that thought was brewing in your mind. So the rank is 4. I'm going to write that over here. What will be the density now, people? Density will basically now be 4 times the mass of one atom. Yeah. Please take it in grams. See, blue and red both are selected, so randomly blue came over here. Fine, let it be now. 4 times the mass of an atom in grams, you know how to calculate that in grams, divided by the volume, that is E cube once again. No need to remember the formula. What was the formula? That was rank into mass in AMU divided by Avogadro's number into edge length cubed. This was the formula. But no need to remember that. Okay? Forget about it. Basic logic is more than sufficient for us. That would be the density. What will be the volume of the atoms? Volume of the atoms would be 4 times the volume of each atom. If the radius of an atom is R, 4 into 4 by 3 pi r cube, because there are 4 atoms inside the unit cell effectively. Now, my dear friends, over here, we need to find a relationship between the radius of the atom and the edge length. Okay? So, this is your edge length, E. This, my dear friends, is R. Can you tell me, okay, let me draw this part again. Can you tell me What's the length of this face diagonal? So the line that I've drawn over here is essentially what? It's a face diagonal. And it's very simple to figure out the length. Okay, this is E, this is E. Use the Pythagorean theorem. Yes, this is E. This is also E. So using the Pythagorean theorem, okay, this squared is equal to this square plus this square. Kitna aa gaya? Face diagonal, basically the length of face diagonal equal to root 2E. Basic mathematics, right? Pythagorean theorem. Why? Because this is 90 degrees. No need to go so deep into it. So this is root 2E, the face diagonal. Okay. Now on the face diagonal, can you recognize how many radii are there? Hoja switch. On the face diagonal, can you see how many radii are there? 1, 2, 3, and 4. Very obvious, right? On this face diagonal, there are 4 radii. 1, 2, 3, 4. So can I write 4 times R is equal to root 2E? Nothing complicated. All of these atoms are basically of the same kind. Okay? All of the atoms that are in there are of the same kind. We've just cut them for the illustration. Okay? All the atoms are the same basically. So on one face diagonal, I can see that 1, 2, 3, 4 of the radii exist. Therefore, 4 are equal to root 2E. Okay? So over here, can I write R is equal to E divided by 2 root 2? You understand how I wrote that? 4 is equal to 2 into 2 root 2. ये कट जाएगा. This will also become root 2 root 2. Okay, fine. In case any of you had that confusion. So R is equal to E by 2 root 2. So can I put that value over here now? So this basically becomes 4 into 4 into, let's just write 16. Okay, 16 by 3 pi E cube by 2 root 2 cube. ठीक है ना? Fine. What's the cube of 2 root 2? What's the cube of 2 root 2? 2 cube into root 2 cube. So 2 cube is basically 8 and root 2's cube is basically again 2 root 2. मैं लोग कट गया यहाँ से चुपचाप. So my dear friends, the volume of the atoms comes out to be how much? Volume of the atoms comes out to be E cube into pi by 3 root 2. This is my volume of the atoms inside FCC in terms of the edge length. Volume of the unit cell, everyone knows, is edge length cubed, E cube. So what's the packing efficiency? What is the packing efficiency? Packing efficiency comes out to be, bhai koi to pen chal pada. Packing efficiency comes out to be how much? Yeah, occupied volume divided by total volume. So that is pi E cube upon 3 root 2 divided by E cube. E cube cancels out. Packing efficiency, the fraction is equal to pi by 3 root 2. But I want to turn this into percentage, so I'll just multiply this with 100. So this comes out to be my packing efficiency percentage. My dear friends, what is this value equal to? Can you calculate this, please? This comes out to be 74.05%. Just remember 74%. Okay, so the packing efficiency of FCC is 74%. 74% of this volume is occupied by atoms. The remaining is empty space. Okay? So can you see that this is packed much more efficiently compared to a simple cubic unit cell? That's very obvious from the data that we have. FCC, face-centered cubic, analysis is done. Rank is 4, density we can always calculate, mass per unit volume. Volume of the atoms is equal to pi e cube by 3 root 2. You don't need to remember this, okay? You can always derive it if you want. Very simple. Okay? And volume of the unit cell we know. So when we divide these two volumes, we get the packing efficiency. Please try to remember the number 74% over here. That number is important for us. Please try to remember 74% packing efficiency for FCC. Chalo, let's move on. Body centered cubic. Okay, this one is body centered cubic. I'll write that over here. This is body centered cubic unit cell. So I can also call it BCC. What's the rank? For the corners again, you have 8 atoms, 1/8 contribution of each. This is 1 plus 1 guy at the body center. There's just 1 atom at the body center, right? 1. So this is equal to, so the rank of a body centered cubic is 2. There are 2 atoms effectively inside 1 unit cell. What would be the density now? The density would be equal to 2 times mass of 1 atom in grams divided by edge cubed. Simple. No rocket science over here. So ye bhi ho gaya. Now what will be the volume of the atoms? The volume of the atoms would be 2 times, because there are 2 atoms in the BCC, 4 upon 3 pi r cube. Now what do we have to do? We have to find out the relationship between R and E. See, this is E. Okay. And if you notice carefully, do you see that here, over here, there is a gap? If you notice the image carefully, there is a gap over here, people. Okay. Because of this gap is significant, by the way. It looks small over here, but it's significant. Because of this gap, I cannot say that R is equal to E by 2. This information is wrong now, because there's a gap over here. Okay, there is a gap over here. So what we need to figure out now is the relationship between E and R. It's not as simple as the simple cubic case. It's not as simple as the face-centered cubic case. There's more to it in this particular system. Fine. How do we figure out? My dear friends, notice, okay, this is one corner, this is one corner, this is pointing towards you, this is pointing a little away from you. Can you see these are touching? These are touching. If I am able to find out the length of the line that goes from this corner to this corner, yeah, if I can figure out the length of this guy, do you see that this is essentially a body diagonal? Let me give you a better image with which you can visualize. See this one only. See this image. Okay, no need to go to any other page. We have that image over here. This one, and this one are on one line. This is just a ball stick model. Okay, so these points are mentioned over here. These are the points where the atoms are, and when you put the atoms at these points, this is what it looks like. Okay, the spheres of the atoms, this is what it looks like. And basically the atom over here will touch the atom over here, will touch the atom over here. Okay, fine. So essentially, my dear friends, this body diagonal has these 3 atoms. Body diagonal has these 3 atoms, isn't it? How many radii are there on the body diagonal? How many radii are there on the body diagonal? So this is essentially your body diagonal, imagine. Okay, this is your body diagonal, and on the body diagonal I have Yeah. I have this part of one atom, rest of it is outside. We don't need to worry about it. Then we have one entire atom in the center, and then another one over here. Let me extend the body diagonal a little just for ease of drawing. Okay, and then there's one atom over here. So my dear friends, now do you see how many radii are there on one body diagonal? 1, 2, 3 and 4. Like in the case of face-centered cubic, 4 radii were there on the face diagonal. Over here, 4 radii are there on the body diagonal. Simple. Now we need to figure out the length of the body diagonal. Okay. For that, let me take you to a different image. इस image से काम लेते हैं थोड़ा सा. This image will be helpful for us. So let's focus on this guy. This is E. What's the length over here? This is also E. And the face diagonal, which we can make like this. What will be the length of the face diagonal? Root 2E. We've done that in the face-centered cubic case as well. Now using this, can we figure out the length of this particular body diagonal? Let me use blue pen for that. If I'm focusing on this particular body diagonal, can I figure out the length of this body diagonal? This is the body diagonal. Okay, this is root 2E and this is E. And this is 90 degree. So what's the triangle that we have over here? That triangle over here is something like this. Okay, this is the triangle that we have. E, root 2E, and this is my body diagonal. Ho gaya? So body diagonal is basically equal to the root of this square plus this square. That is 2E square plus E square. That is equal to how much? Fine. So the length of the body diagonal is how much? Root 3E. Let's go back to the previous page. So now I can say that 4 times R is equal to root 3E. Fine, very simple. No rocket science once again. Now our analysis will be simple. Volume of the atoms is equal to 2 into 4 upon 3 pi r cube. I can substitute the value of r over here now. 2 into 4 by 3 pi into r is how much? Root 3 by 4 e whole cubed. ठीक है जी, तो इसको थोड़ा simplify करना तो कर लो. If you want to simplify this, let's do that. 2 into 4 into 3 root 3 into pi into e cube divided by 3 into 4 into 4 into 4. This is what's going on. Just to simplify things. So 4 and 4 will cancel out. 3 and 3 will cancel out. This is 2. 2 into 4 is 8. So this comes out to be root 3 pi e cube by 8. A little fancy, but you don't need to remember this value. Okay, this is just analysis for our understanding. I hope you're doing it with me in your notebooks as well. Volume of the unit cell we know E cube. So packing efficiency, just divide both of those. Divide this and divide that. So E cube will cancel out essentially. So packing efficiency over here is root 3 pi by 8. And if you want to convert it into a percentage, just multiply that with 100. My dear friends, what does this value come out to be? This comes out to be approximately 68.02%. Again, the 02 is not important over here. 68% packing efficiency in the body-centered cubic case. If at any point you have confusion, just rewind the video a little and watch it again. It's all about imagination, no rocket science. I'm repeating that again. Now people, let's do a quick summary of what we have figured out till now. Please make this table with me in your notebooks. Simple cubic, face-centered cubic, body-centered cubic. For all of these cases, we will try to write the rank. We will try to write the packing efficiency, and we will also write what's the relationship between R and the edge length. R is the radius of an atom, E is the edge length of the unit cell. Okay, so for simple cubic, the rank is 1. Packing efficiency is how much? 52.4%. Yes. And what is the R versus E? R is basically equal to E by 2 from the image that we had seen. Phase standard cubic, rank is 4. Packing efficiency 74%. Maximum amount of packing efficiency out of all of these is in FCC. Okay, and what is R versus E over here? R is basically equal to root 2E by 4. Yes, face diagonal divided by 4. R is equal to root 2E divided by 4. Okay, and then BCC, what is the rank? The rank is 2. Packing efficiency is 68%, and R versus E, radius is equal to the body diagonal divided by 4, root 3E by 4. Done. Now, let's move on to some questions. We'll do 2-3 questions and that's it for this class. An element has body-centered cubic structure. Areva. An element has body-centered cubic structure, okay, with a cell edge of 288 picometers. The density of the element is 7.2 grams per cubic centimeters. How many atoms are present in 208 grams of the element? Let's try to solve the question. So in order to solve these questions, please write down all the information that they've given us, okay? So first of all, it's body-centered cubic, yes? So this means what is the rank? The rank is equal to body-centered cubic, rank is 2. Edge length is 288 picometers, so E is equal to 288 into 10 to the power minus 12 meters, picometers. The density of the element is 7.2 grams per cubic centimeter. So density, which is equal to mass upon volume, is given as 7.2 grams per cubic centimeter. You can write cc as cubic centimeter, or you can do centimeters cubed. This is in meters, this is in centimeters. Either you convert this into centimeter or you convert this into meter, okay? I think it's easy to convert this into centimeter, okay? So 1 meter is equal to 100 centimeter. Everyone knows this. So replace the M over here with 100 centimeter. So these two zeros will get multiplied over here. So I can simply write it as 10 to the power minus 10 centimeters. Just converted picometers into centimeters. Units have to be similar throughout. Now, my dear friends, this can be written as, for BCC, what can I write it as? I can write it as 2, that is rank, into the mass of one atom. Yes, divided by edge length cubed. This is also given to me. ये भी दे रखा है. I can write it as 288 into 10 to the power minus 10 centimeter cubed. From here, do you realize I can calculate the mass of one atom? If I can calculate the mass of one atom, total mass of atoms is given. Number of atoms will be equal to total mass divided by mass of one atom. Isn't it? This is total mass. Mass of one atom can be calculated from here. This, my dear friends, will be our answer. So you see in this question, by simply writing out all the information that we have, we got to the answer. So the thought process of solving this question becomes simple when you write down all the information. Now all you need to do is just plug in the values, right? This is how you're supposed to solve this particular question. Please do it yourself. The calculation is a bit too lengthy. I'm sure you'll be able to do it. And again, this is an NCERT example. Okay, this is given in the NCERT as well. So figure out the answer. This is approach number 1, by the way. There's another approach of solving this question. This is approach 1. Total mass by mass of one atom is the first approach. There is another approach over here. The other approach is also very interesting. Okay. The other approach is also very interesting over here. My dear friends, what's the volume of 1 unit cell? Volume of 1 unit cell is E cube, which is given as 288 picometer. Just, I'll write it like this. Okay, this is volume of 1 unit cell. Now, total volume. How do I calculate total volume? Now, for calculating total volume, I can use density. Okay, density is equal to mass upon volume. So I can write volume is equal to mass, total mass upon density. Yes, total mass is given to us as 208 grams of the element. Okay, that's the total mass. So I can write volume is equal to 208 divided by the density, that is 7.2 grams per cc. This gives me the volume. Yes, this gives me the volume 208 by 7.2. This gives me the total volume. So now, my dear friends, over here from this information, can I say that the number of unit cells is equal to total volume upon volume of 1 unit cell? Isn't it? Total volume is this one. Volume of 1 unit cell is this one. Divide, you will get the number of unit cells. And also, you know that for BCC, there are 2 atoms per unit cell. So you get the number of unit cells over here, you multiply the number of unit cells with 2, you get the atom. So this is another approach. Okay. Total volume by volume of 1 unit cell is another approach. So what was the previous approach? Total mass by mass of 1 atom. This approach is total volume by volume of 1 unit cell. Both of them can be approached via density. Okay. Try both of these approaches. Calculate the answers over here. Leave the answer in the comment section. That will also be fun. Now, let's solve this particular question. Fine. Over here, we can use approximation. Very nice. An element with molar mass 2.7 into 10 to the power minus 2 kilograms per mole forms a cubic unit cell with edge length 405 picometers. If its density is 2.7 into 10 to the power 3 kilogram per meter cube, what is the nature of the cubic unit cell? Basically, they're asking, is it simple cubic? Is it FCC? Is it BCC? And the easiest way to figure that out is to calculate what's the rank. How many atoms are there inside 1 unit cell? If we can figure that out, we would know whether it's FCC, BCC or simple cubic. So let's just write all the information that we have and I think we'll have the answer. Density se solve karte hain isko. Let's solve it via density because density is given. So my dear friends, I can say that density is equal to the rank into mass of 1 atom divided by edge length cubed. Let's write it down. Density is given as 2.7 into 10 raised to the power 3 kilograms per cubic meters. This will be equal to Z, which is something that we don't know. Z bole to rank. Mass of 1 atom, it's given to us 2.7 into 10 to the power minus 2 kilograms per mole. Please don't forget this. What is this mole? This mole is basically 6.022 into 10 to the power 23 atoms. Don't forget this. It's given in the unit. Kilogram per mole. Always take care of the unit. Your answer will be correct. Then you have edge length cube, that is 405 into 10 to the power minus 12 meters cubed. Don't forget to convert picometers into meters also. Now it's just about calculating Z. So Z will be equal to how much? let's just write all the numbers. Okay, so Z will be equal to 2.7. Acha, 2.7 and 2.7 cancel each other out. Simple. This will be equal to 10 to the power 3 into 405 cubed into 10 to the power minus 36. 12 into 3 is 36. Okay. Then you have 1 mole, that is 6.022 into 10 to the power 23. Fine. Now meter cube and meter cube cancel each other out. Kilogram and kilogram cancel each other out. Basically, rank is a dimensionless quantity. It's just a number of atoms inside a unit cell. Okay. So this is the calculation that we have to do. Did I forget anything? Here, 10 to the power minus 2. 10 to the power minus 2. If I take this upstairs, this will become 10 to the power 2. Let's add it to this 3 and simply write this as 10 to the power 5. This is the calculation that we have to do. We can approximate it, by the way, because we know the answer will either be 1 for simple cubic, either the answer will be 4 for face-centered cubic, or the answer will be 2, which will give us body-centered cubic. Since we know the answer is either 1, 2 or 4, we can approximate it and see what's the nearest number out of those 3. So now let's just approximate this jazz. Okay, please switch to blue pen, you weird whiteboard. Blackboard, sorry. हाँ जी, तो क्या करें यहाँ पे? This becomes 10 to the power minus 31. Okay. Isko, let's just try to approximate this. So let's approximate it as 400 cube. 4 into 4 is 16, into 4 is 64. So 64 into 10 to the power 6. Yeah. Basically 4 cube into 100 cube. So 4 cube is 64, 100 cube is 10 to the power 6 into 10 to the power minus 31 into 6.022 into 10 to the power 23. Just do whatever you want to the powers of 10. You can simplify or just do this calculation. Okay, 64 into 6. How much is 64 into 6? 6 into 4 is 24. 36, 37, 38. Something. Okay. Now if you simplify the powers of 10, the answer will come out to be 3.84. That's a logical idea. Why is this logical? See, because the answer has to be either close to 1 or close to 2 or close to 4. Those are the possible ranks. 1, 2 or 4. This is the only number that will be close to 4, right? You can, if it's too much information for you, if it's too confusing, just simplify the powers of 10. You will be remaining with what? Minus 31. 6, 7, 8, no. 29, 31. 10 to the power minus 2 is remaining. Yeah. So 64 into 6 is 384 into 10 to the power minus 2. That is 3.84. This is an approximate calculation. If you do it accurately, you will basically come up with 4. Rank is 4, therefore this is face-centered cubic. Ultimately, you just had to calculate the rank. We've done some approximation over here. And we can do the approximation because we know the answer has to be either very close to 1 or very close to 2 or very close to 4. Those are the only 3 options. Chalo ji, this is done. Very nice. Okay ji. So today's class is done. Questions are also done. This one, please give me the answer in the comment section down below. Calculate the number of atoms, please. So my dear friends, I hope you enjoyed today's class. Nice and fun, nice and conversational, nice and simple. Not too long, I hope. So if you did, make sure you hit the thumbs up button, stay subscribed to the channel. The next class of solid state will be very important because we'll talk about packing efficiency and voids. That is the most complicated class of solid state to understand. Then just one more class talking about defects. So 2 classes of solid state are remaining. So the next class will be there on Monday again at 8 p.m. and the final class for this will be on Wednesday at 8 p.m. I'm going to see you in the next one. Until then, bye bye.